This is E5B cost estimation using the power sizing model. If you recall, in E5A, we had information about what something had cost in the past, and we were able to leverage that using a price index to find out what something might cost today. So that's a very useful way to go about estimating cost. But another possibility is we don't know what something of a particular size might cost, but we do know something about what a plant, say, of a different scale had cost. So we're going to ignore the possibility that the original plant was built in a different time period, in which case we would have to also employ a price index, and we can maybe mention that at the end. But let's start out with the issue of scale, which economists recognize as saying that we're in the long run where all factors are variable. So we have C is the cost in dollars of a particular plant size. Let's say we know what B is. So we know B, and we want to find the cost. We know the cost of plant size B, and we want to find the cost of plant size A. So this is the known variable because we already have a plant, say, of that size. And we're thinking about building another plant, and we'd like to know what that would cost, but it's a different size. All right, so S stands for size. X is something called the power sizing exponent, and it's going to differ depending on exactly what type of process we're talking about. It's possible that X is 1. This is called constant returns to scale. And all that says is, for example, if you doubled the size of the plant, the cost would exactly double. Very common in many manufacturing processes, X would be anticipated to be less than 1. This is called economies of scale. That says if you doubled the size of something like a factory, you would anticipate that costs would less than double. And finally, somewhat less common, I would say, and that's the example we're going to use in this video. You could have diseconomies of scale. In that case, X would be greater than 1, and that would just say that if you double plant size, cost would more than double. And you're probably thinking, where would I get these X's from? Where would I get the power sizing exponent? And these are published by industry groups, and you can track them down if you were working. Somebody would probably tell you where to find them, so don't worry about that. One of the textbooks, Noonan et al., has reproduced a very small table of some of these power sizing exponents from various processes. And I thought that for fun, because diseconomies of scale is a little less common, we would use the example of the aerated lagoon. And economists are probably thinking, what on earth's that? Well, it's a wastewater treatment process. It's a pond, you pump air in, the bacteria eat all the nasty stuff, and you have clean water. So it's a lovely, simple process. And if you look at the examples of power sizing exponents from the Noonan book, the aerated lagoon has a power sizing exponent of X equals 1.13. So as I said, because that's greater than 1, this must mean that this is a process that if you double the size of the aerated lagoon, then the cost is going to more than double. So we have diseconomies of scale. Okay, so then we have to give ourselves some more information. Suppose we have a 1 million gallon aerated lagoon, and it cost $200,000. I don't actually know what they cost, but let's just go with that. So let's say it costs $200,000, and we want to know, so this is something we know, you would be given this in the question, and what we want to find is we would like to know what it would cost to have a 2 million gallon lagoon. We don't know that. We're going to use the information from the power sizing exponent and the information we have about a 1 million gallon lagoon to figure out what a 2 million gallon lagoon should cost. So we're interested in that. So let's let's take a look at this. So we have CA over CB, cost of A over cost of B will be equal to the size of A. So that's going to be 2 million. We want to know what that would cost divided by 1 million. And the power sizing exponent is 1.13. So this, of course, is the relative cost of A to B is going to be 2 to the 1.13, which turns out to be, if you can check that if you like, is 2.188. We'll go with all the decimal places because we've got them. 1.88587. So cost of A, which we don't know, will be equal to $200,000, which is the cost of B, which we do know, multiplied by 2.18887, which is $437,717. So you can see that you've got the diseconomies of scale because you doubled the size, but the cost more than doubled. So that's the power sizing model. You would be given the power sizing exponent, so it's, conceptually very simple. The possible wrinkle if you were doing a question like this is it might turn out that the question says, well, we put in the original aerated lagoon in 2005, and then now we're trying to build a bigger one in 2015. If you get that type of question, you're going to start out using the power sizing exponent and find the cost. And so essentially what you would have done at that point is you would find what a 2 million gallon lagoon would have cost in 2005. So that, that's fine. But then you're going to, then the question would then tell you something about the prices, and you would need a price index, and you can go back to 5A how to do that. But you could take this 437,717, use the price index you were given to say what would a lagoon that's twice as big and built this year instead of 2005 would cost. So then you would have to employ the two different techniques in order to come up with an estimate for this year. So hopefully that's helpful, and see you in the next video.